Hello everyone, welcome to our channel Mathematics Pathshala. This is a CSIR NET question of 2023 June and this is our question ID. So let us now try to solve this problem. Consider R with the usual topology and then which of the following assertion is correct. See here, four options are given and only option 2 will be right and 1, 3 and 4 will be false. So first we will discuss that why 1, 3 and 4 are false, and then we will see that why 2 will be right. So to prove this, we need to note that any T1 topology on any finite set will be equal to the discrete topology. So let us first prove that result. So I am saying that if X is any finite set and tau is a topology on X such that tau is T1, then tau will be equal to the discrete topology on X. See, first we know that there is a result which is a if and only if criteria for to be T1, that any topology for any topology tau is T1 if and only if every singleton set in X is closed. That means for any X belongs to X, singleton X is a closed set. Thus, it will imply that every finite set is closed. It will imply that every finite set in X is closed. Why? Because if we take A any finite set, then we can express A as the union of singleton elements of this set. X belongs to A and all these singleton members are closed, and since this is finite union of closed set, it will be closed. So we have that our topology tau is T1 if and only if every finite set in X is closed. Now see that if we take X a finite set and tau a topology on X which is T1, we now prove that tau will be equal to the discrete topology on X. So to prove this, we need to prove that all sets are open sets. So suppose since X is finite, we can see X as x1, x2 dot xn and take any xi belongs to X, and first we now prove that this is an open set. This is an open set. We will prove that this singleton xi belongs to tau. So for this, consider the set x1, x2 dot xi minus 1, xi plus 1 up to xn. That means actually this is x minus singleton xi. So clearly this x minus singleton xi is finite set because X is finite, and we now prove that we have just proved that every finite set is closed. So this X minus singleton xi is closed and hence its complement, that means singleton xi, is open. So this belongs to tau. And exactly in a similar manner, all the singleton sets of X are open, and hence any subset of X is open, because if we take any subset A of X, then we can express A as union of singleton members x belongs to A, and also we know that arbitrary union of open set is open. So since all these singleton sets are open, A will be open, and we have taken A an arbitrary subset of X. So what we proved that any subset of X is open. So this tau becomes equal to tau D, discrete topology on X. So any T1 topology on any finite set will be equal to the discrete topology. Now see the options. 1. A finite set containing 33 elements has at least 3 different Hausdorff topologies. Hausdorff topology means T2 topology. So since this is a finite set, and if we take any Hausdorff topology on this set, then that topology must be T1, and hence that topology will be equal to the discrete topology on that set. So there cannot be two topologies. There cannot be two different topologies which are T1, because any topology which is T1 on any set containing 33 elements, that will be equal to the discrete topology. So exactly one topology is there which is discrete topology, which is T1. Then comes to the option 3. See, let X be a discrete topological space having infinitely many elements, and f R to X be a continuous function, G X to R be any non-constant function, then the range decomposition F contains at least 2 elements. So it is a very easy to see that this option may not be true, because if we define a function f R to X, take any x0 belongs to X be arbitrary and but fixed, then define f A equal to x0 for all A belongs to R, that means f is constant function, and define G from X to R by Gx equal to say 0 for all X not equal to x0 and equal to 1 if X equal to x0. Now clearly G is non-constant. Now see what will be our decomposition F. So decomposition F function will be actually from R to R, and decomposition at A equal to any for any A, G at FA, and FA will be our x0 for any A belongs to R. So G at x0, and that will be our 1. So for any A belongs to R, decomposition FA at 1. So range of this decomposition F will be equal to singleton 1. So there exists exactly one element. So this set contains at least 2 elements will be the false option. Now comes to the point 4. See, if a non-empty metric space X has a finite dense subset, then there exists a discontinuous function f x to R. We now prove that all functions from X to R will be continuous, because if we take X a metric space, then X must be T5. So we need only T1. X is T1. So X has a finite dense subset. So consider A is that finite dense subset. So A is finite and A is dense. Dense means A bar equal to X. And since X is T1, every finite set is closed. So A is closed and A equal to A bar. So A equal to actually X. So X is finite. Since X is finite and also metric space, so it is T1. So there exists, this is actually discrete topology is there. And since this discrete topology is there, any function from X to R will be continuous. So there cannot exist any discontinuous function. Now we will now see for the option 2, if X is a non-empty set with Hausdorff topology, that means T1. So there is discrete topology, and similarly X cross X will be with discrete topology, product topology will be discrete topology. So any function from X cross X to R will be continuous. So option 2 will be true and others 1, 3, 4 will be false. This is another CSIR net question of 2023 June, and this is 704089 is our question. This is question ID. and the problem is seen here. This is another problem on topology. Which of the following statements are correct? Option 1 says that the set of open right-half planes is a basis for the usual topology on R2. Number 2 says that the set of lines parallel to y-axis is a basis for the dictionary order topology on R2. Option 3 says that the set of open rectangles is a basis for the usual topology on R2. And option 4 says that the set of line segments without endpoints parallel to y-axis is a basis for the dictionary order topology on R2. First of all, we will see about the usual topology. It is in option 1 and option 3. So look at option 3. The set of open rectangles is a basis for the usual topology on R2. We know that in R, open intervals, the collection of all open intervals will form a base for the usual topology on R, and also we know that the collection of all open disks, the collection of such open disk, interior of the circle open disk will form a base, for the usual topology or Euclidean topology on R2. And see here, if we let script BU is the collection of all such open disk and script BR is the collection of all open rectangles on R2, and if we say that if we let that script BU forms script BU generates the topology tau u, that is our usual topology or Euclidean topology on R2, and if we let that script BR generates the topology tau R on R2. Now we will show that this tau u and tau R will be same. There is a result, the comparison of two topologies with the help of their bases. So first of all, if we take any such element in script BU, that means any open disk, and any element x from here, then easily we can find an open rectangle in this area. So this means that this script BR generates the larger topology. That means we will get tau u subset of tau r. So that is why actually we have done. We have taken an element, say B1 belongs to script BU, and we have find an element B2 belongs to script BR such that this x belongs to B2 subset of B1. It means that tau r will generate the larger topology. And exactly in a similar manner, if we take an element script BR, that means an open rectangle, and any element y from here, then easily we can find an open disk which lies entirely in this open rectangle. That means this script BU generates the larger topology. So tau r is subset of tau u. So we have tau u equal to tau r. So which we have now get that if this script BR is the collection of all open rectangles, then this script BR generates the topology tau r, which is equal to actually tau u usual topology. So the collection of all open rectangles will generate the usual topology on R2. That means this is the basis for the Euclidean topology on R2. So option 3 is right. Option 3 is right. Now look at the look at option 4. Look at option 1. Here says that the set of open right half planes is a basis for the usual topology on R2. We all know about the definition of a basis. Just remind that a collection script B of subsets of a non-empty set X is said to be basis if number 1, for any x belongs to x, there exists an element b belongs to script b such that x belongs to b, and number 2, if we take two elements b1, b2 belongs to script b with x belongs to b1 intersection b2, then there exists another element b3 belongs to script b such that x belongs to b3 is subset of b1 intersection b2. So if a script b, a collection of subsets of x, satisfies these two conditions, then we will say that script b is a base for some topology on x. Now again look at the option 1. The set of open right half planes is a basis for the usual topology on R2. So we now show that option 1 will not be correct. So consider in R2, consider two right half planes. Number 1, B1 is considered that this right half planes, that xy belongs to R2 such that x greater than 0, that means in this area, x greater than 0 in this area, and consider another right half planes B2 equal to the collection of all xy such that y greater than 0, that means in this area. So clearly here our B1 intersection B2, our B1 intersection B2 will be this area, that xy belongs to R2 such that x greater than 0 and y greater than 0. The area in first quadrant excluding this x axis y axis. So now we will show that option 2 will not satisfy. So take any point from here, take any point x comma y, from B1 intersection B2, and to satisfy script B is a basis, we need to find another element B3 such that x comma y belongs to B3 should be subset of B1 intersection B2. But see, there is no such right half planes which will be entirely contained in this first quadrant, because if we take such these right half planes, then this plane, there will be point here, there will be point in this area in B3, and which will not be in B1 intersection B2. So we cannot find a right half plane which contains x comma y and which will be subset of B1 intersection B2. So this script B, the collection of all such right half planes, will not form a basis, will not form a basis for the usual topology on R2. So option 1 is not correct. Now look at option 2 and option 4. This is about dictionary order topology on R2. See, first we will see the basis, the base of the dictionary order topology on R2, and see the figure here. This is from the book Bankresh, this figure. So here says that this two type of collection, see here, if A less than C, then this collection of this type of lines, and also from this figure, this type of line segments parallel to y-axis, if A equal to C, this is without the endpoints. So these two, the collection of these two types, the sets of collection of these two types will form a base for the dictionary order topology on R2. And also see here the sub collection of these two collections, that means only if we consider only this type of collections, that means this type of line segments parallel to y-axis without the endpoints, this type of collection also forms a base for the dictionary or topology on R2. And see here we have one option here that the set of line segments without endpoints parallel to y-axis is a basis for the dictionary or topology on R2. So our option 4 is correct. And now we will show that option 2 will not be the correct answer. See here says that the set of lines parallel to y-axis is a basis for the dictionary or topology on R2. So we now show that if we consider the collection script B of all the lines parallel to y-axis, then script B will not form a base. So to show that we need to show that if script B is a base, then what is the condition to be a base? That if we take any open set, say U belongs to that topology say tau, then we have to find a member B belongs to script B such that this B subset of U. So we now show that this condition will not be true. So first of all, we have this type of collections of by option 4, and also written here that if we consider the collection say script B2 of all such line segments parallel to y-axis without the endpoints will form a base for the topology tau. And clearly then script B2, that base is a sub collection of tau. So all the members of script B2 will be open set. So consider one element, one such line segment, from this script B2 and say U equal to our this line segment. So to be script B is a base, what we need to find a member B belongs to script B such that this B should be subset of U. But see, this B consists of members which are only the lines parallel to y-axis, and this U is the only a line segment parallel to y-axis this type. So any member B belongs to script B, that means any line which is parallel to y-axis cannot be a subset of this line segment U. So this script B does not form a base for the dictionary or topology on R2. So option 2. And this is another problem on CSIR UGC NET June 2023, and 704090 is the question ID. And this is another problem of topology. See the question here. X equal to pi n equal to 1 to up infinity 0 1, that is the space of sequences xn with xn belongs to 0 1, n greater than equal to 1, and the metric D from x cross x to 0 infinity is defined by this sup metric. And then which of the following statements are correct? Metric topology, number 1, metric topology on x is finer than the product topology on x. Metric topology on x is coarser than the product topology on x. The metric topology on x is same as the product topology on x. And the last one is the metric topology on x and the product topology on x are not comparable. See here, 0 1 is the subspace of the usual topology on R. So we will see 0 1 as the subspace with respect to the usual topology on R. So this is the countable infinite product of the 0 1, which is the subspace as the usual topology on R. And we now show that the metric D is defined here in this way, and we now show that the topology induced by this metric will be the same as the product topology on X. So we now show that the product topology on X and the metric topology on X will be the same. So our option 1, 2, 3 will be correct and option 4 will be false. So let us now start to show this. And before starting, we need to write important result which will help to serve our purpose. That suppose X is a non-empty set and tau 1, tau 2 are two topologies on X, and script B1 and script B2 with the bases for the topology tau 1 and tau 2 respectively. For the topology tau 1 and tau 2 respectively. That means beta 1 generates tau 1 and beta 2 generates tau 2. Now the theorem is about to the comparison of tau 1 and tau 2 with the help of their bases. So now tau 1 will be subset of tau 2, that means tau 2 will be stronger and tau 1 will be coarser if and only if for any B1 belongs to script B1 with X belongs to B1, there exists a member, say B2 belongs to script B2, such that X belongs to B2 subset of B1. That means if we take any basic open set B1 and any X here, then we can find a basic open set B2 from script B2 such that X belongs to B2 is subset of B1. If we can do that, then we will say that tau 2 will be the stronger topology than tau 1. So this will be a important result which will be used here to show that, because we now show that the product topology and the metric topology will be equal. So let us now denote the metric topology by, let us now denote the metric topology by tau d and script bd with a base for tau d, and we denote product topology by tau and script b for the base which is the base for tau. So this will be our notation, and what we need to show is that tau equal to tau d, then our problem will be solved. So to show tau equal to tau d, we first show that tau d subset of tau, and then we show that tau subset of tau d, then it will be equal. So first, to show tau d subset of tau, we need to take a basic open set in the product topology tau. Sorry, we need to take any basic open set for the metric topology tau d. So let us take an open set B belongs to script bd, which is the base for the metric topology tau d, So clearly this B, since this is a basic open set in the metric topology, so this B will be of the form B equal to, say, bd x epsilon for some positive epsilon greater than 0. Now choose n large enough such that 1 by n less than epsilon. We can choose such n by Archimedean property. Now let us take V equal to, say, x1 minus epsilon comma x1 plus epsilon open interval Cartesian product x2 minus epsilon x2 plus epsilon dot dot up to say xn minus, for this n, xn minus epsilon xn plus epsilon, and the other product will be same as 0 1, 0 1 cross 0 1 dot dot. So first we have taken b belongs to script bd with x belongs to b, with x belongs to b, x is our sequence xn. So first we have seen that this basic open set will be of the form bd x epsilon for some epsilon greater than 0, and then we have chosen an n such that 1 by n less than epsilon, and we have taken a set v equal to this. So we now show that x belongs to v is subset of this bd x epsilon. So clearly this x belongs to v, this is very clear because this x equal to xn, and x1 is here, x2 is here for these coordinates, and after nth coordinate this 0 1 will be the in the product. So clearly x belongs to v, and we now show that v is subset of bd x epsilon. For this, let us take an y belongs to v. So this y equal to our sequence yn. So clearly our y1 belongs to, in the first one, x1 minus epsilon, comma x1 plus epsilon. Second one, y2 belongs to x2 minus epsilon, comma x2 plus epsilon, and up to yn belongs to xn minus epsilon, comma xn plus epsilon, and the rest elements yn plus 1, yn plus 2 dot dot all are belongs to closed interval 0 1. Now see, for the first n coordinate, first capital N coordinates, yi belongs to clearly xi minus epsilon, comma xi plus epsilon. That means our mod xi minus yi less than epsilon for all I less than equal to n, and also 1 by 2 to the power I mod xi minus mod yi less than epsilon by 2 to the power I less than epsilon for all I less than equal to n. And then for I greater than n we will now calculate. So for all I greater than n, see 1 by 2 to the power I less than 1 by I less than 1 by n. And also, since this xi, yi are taken from closed interval 0 1, because all coordinates are taken from open interval, closed interval 0 1, so our mod xi minus yi will be less than equal to 1. So for all I greater than n, 1 by 2 to the power I mod xi minus yi will be less than equal to 1 by 2 to the power I, and which is less than 1 by n, which is less than 1 by n. And also we have taken n such that 1 by n less than epsilon. We have taken so n such that 1 by n less than epsilon. So here this 1 by n less than epsilon. So see, first we have calculated for any I less than equal to n 1 by 2 to the power I mod xi minus yi less than epsilon, and then we have seen that for all I greater than n also 1 by 2 to the power I mod xi minus yi less than epsilon. So what we get, that for any I belongs to natural number, for any I, sup I greater than equal to 1 mod xi minus yi by 2 to the power I less than epsilon, and this is our dxy by the definition of D. So dxy less than epsilon, so our y belongs to this, that means BD x epsilon. So see again that we have taken y, we have taken any y belongs to V, and what we get, that this y belongs to BD x epsilon, and also our x belongs to V. So merging this, what we have get, x belongs to V subset of BD x epsilon, and this we have taken as any basic open set B from our metric topology. And see also the structure of our V, we have taken our V as, see, this is the structure of our V. See, the first coordinate is open set in closed interval 0 1 as the subspace topology. The second one is open set in the closed interval 0 1 as the subspace topology, and this is also an open set in closed interval 0 1 as the subspace topology, and the rest are the whole sets. Rest are the whole sets, and we also know that any basic open set in the product topology is of the form, there are finitely many open sets in finite indices, and the rest will be the whole sets. So this is clearly a basic open set in the product topology. So what we have done, we have taken an basic open set in the metric topology, and we get a basic open set V belongs to our script B, which is the base for tau. So this implies by our result stated above that our tau is the larger topology. So tau D is subset of tau. So one part is our done. Now we will show the second part. Now we will show tau subset of tau D. So for this, we now take any basic open set in the product topology. Let U belongs to our script B, that is the base for the product topology, with our x belongs to U, and we now show that there exists an basic open set V belongs to script BD such that x belongs to V subset of U. This we need to show. So now see that we have taken U, a basic open set from the product topology, and now we have just stated that any basic open set in the product topology is of the form U equal to pi ui, where ui are open for finite indices. Say ui is open in closed interval 0 1 for say I equal to alpha 1 alpha 2 up to alpha n, and the rest ui will be equal to the whole space, that is closed interval 0 1 for all I not equal to in this form alpha k. So we need to show what, that an basic open set V belongs to BD, V belongs to script BD such that x belongs to B subset of U. See here, UI is open, and UI is open in closed interval 0 1 for I equal to alpha 1 alpha to alpha n, and also our x belongs to U, that means our xi belongs to ui, and since this ui is open, so each xi is interior point, so there exist for each I equal to alpha 1 alpha to alpha n, there exist say alpha I greater than 0 such that xi belongs to xi minus epsilon I comma xi plus epsilon I is subset of ui. because this UI is open in the usual topology in closed interval 0 1 as a subspace topology of R. For I equal to alpha 1, alpha 2 dot dot alpha n. Now let us take epsilon as epsilon equal to minimum of this epsilon I by 2 to the power I for I equal to alpha 1, alpha 2 dot dot alpha n. So this is minimum of epsilon 1 by epsilon alpha 1 by 2 to the power alpha 1, epsilon alpha 2 by 2 to the power alpha 2, and so on up to epsilon alpha n by 2 to the power alpha n. And we now show that x belongs to this BD x epsilon subset of our this U. So then we tell this BD x epsilon equal to our that V, which we need to find. We now tell this BD x epsilon as our required V. So we now show that first. So clearly this x belongs to BD x epsilon. This is very clear. So we now show that BD x epsilon is subset of U. So for this, let us take an y belongs to this. Let an arbitrary y belongs to BD x epsilon. So our dxy is less than epsilon. That means our sup 1 by 2 to the power I mod xi minus yi I greater than equal to 1 is less than epsilon. And so that means our 1 by 2 to the power I mod xi minus yi less than epsilon for all I. And also by the construction of epsilon, it is very clear that this epsilon is less than equal to each epsilon I by 2 to the power I for I equal to alpha 1, alpha 2 up to alpha n. So we get from this and this mod xi minus yi less than epsilon I for I equal to alpha 1, alpha 2 dot dot alpha n. And that means our yi belongs to open interval xi minus epsilon I comma xi plus epsilon I, and that is also subset of ui for also I equal to alpha 1, alpha 2 up to dot dot alpha n. And see, now here our y1 belongs to this u1, y1 belongs to I equal to alpha 1, alpha 2, alpha n. So our y alpha 1 belongs to our u alpha 1, our y alpha 2 belongs to our u alpha 2, and dot dot our y alpha n belongs to our u alpha n. And see, in the definition of our u, when I not equal to of the form alpha I, then others are ui equal to closed interval 0 1. So since here y alpha 1, y alpha 2 up to y alpha n belongs to here u alpha 1, u alpha 2, u alpha n, and rest are closed interval 0 1. So clearly the others yk will be closed interval 0 1. So our y will be in this product ui, and that is equal to our u. So we have taken an arbitrary y belongs to BD x epsilon, and we get this y belongs to u. So what we get? We get this BD x epsilon is subset of u, and also clearly this x belongs to here. So this BD x epsilon we say this V equal to this V dx epsilon is clearly a basic open set in the metric topology. So we have taken a basic open set in the product topology and we get a basic open set V in the metric topology, which is subset of that basic open set of the in the product topology. So our metric topology will be larger. So tau, which is the product topology, is subset of tau d, which is our metric topology. So by the previous one, with this we get tau equal to tau d. That means the product topology will be is equal to the metric topology induced by our this given metric dxy equal to sub mod xn minus yn by 2 to the power n. So our here option 1 metric topology is finer than the product topology. Finer means also may be equal. Option 2 metric topology is coarser, that may be also equal, and the metric topology is the same as the product topology, which now we have proved. And option 4 they are not comparable is the not correct option. So option 1, 2, 3 is the right option. Thank you.